guys. So, welcome back from Thanksgiving break. I hope everybody had a fabulous holiday. I hope you guys stuffed your bellies, and I hope that you had a good time with your family, or at least able to talk to your family during this time. So, we're going to get right back to the grind of things, and we're going to start with talking about how they organized the periodic table and how scientists back then took these elements without much knowledge about them and were able to organize stuff and get it in a systematic pattern, okay, that we still use today, which is kind of fascinating that back then, when they had such limited knowledge on how to do things, they were able to come up and find ways to organize the table in these certain situations. So chemists used the properties of elements to sort them into specific groups, like categories of groups, okay? And as you can see right here, you just got done doing the periodic table, in which you were kind of getting to know things about the periodic table, like where are the metals, where are the non-metals, what are semi-metals, what are synthetic elements, where are my gases at room temperature, where are my solids, liquids, and so on. We learned about how they were categorized by names. So there's families of names of alkali metals, alkaline earth metals, halogens, noble gases, how they react with one another. Okay? Now, there was, you should know, because you've been going up all through the years in science, learning about Dmitry Mendeleev, who was a Russian chemist, right? And he is credited with creating the first useful periodic table. He arranged the elements in order of increasing atomic mass, and he also put elements with similar properties in the same group. So this picture right here is actually the original table of the periodic table, okay? How Mendeleev began arranging these elements. Now, at that time, these were the only number of elements that had been discovered. Okay, there were several elements that hadn't even been discovered yet, and that's why the table looks small in size. Now, so he started putting these elements together and sorting them into specific groups based on their properties, experiments that he would run, and putting them in these set groups by the conclusion of what he saw within the different reactions. Okay, so what he could conclude from observing the different reactions, like if this particular element would react with this substance, or what was the weight, or did it melt at a low melting point or a high melting point, and so on. So he started taking these different categories and sorting them, okay, and then moving them around and trying to come up with a set table. Now, when he finished sorting these, he noticed that there were blanks in certain spots, okay? And he said, you know, I feel like there's going to be an element later on, okay, that we have not yet discovered that's going to fill that spot. So he actually left blanks within the table, saying at some point we're going to get to a point where we find an element that will fit in that category. Now, since he arranged his periodic table based on properties, he predicted the properties of elements that had not been discovered. So where these blanks were located within his table, he was able to predict the outcome of what that discovery was going to be later down the road. When the elements were discovered, his predictions were correct. He was 98% accurate. And when I say accurate, he was able to predict germanium, okay, the element we see underneath silicon. He knew that there was an element between silicon and tin, because they actually had those elements discovered. But there was not the element between, which we later know now as germanium. It was discovered in Germany. But he called it ecosilicon, which means after silicon. And what's fascinating is he predicted what the atomic mass would be. He predicted the melting point. He predicted the color of what it would look like. He was able to predict what elements it would react with, what it would dissolve in, and so on and so on. So all of these characteristics about an element that had never existed at that time, he was able to predict properties based on the properties of silicon and the properties of tin. So that started getting scientists thinking, wait a minute, there's a vast number of elements out there on the periodic table that we've not yet discovered, but wow, we can just like start looking at other elements within the same column and start predicting that this was going to happen. Now, the modern table that we see today is arranged by atomic number. Now, how did that change? Why did it flip from atomic mass that Mendeleev originally did to the atomic number? Well, what happened was, as Mendeleev was arranging this table in order of atomic mass, there were a couple elements that flipped, such as tellurium and iodine, Te and I. When he was arranging them by atomic number, he noticed that they were flipped. But then as he started studying the properties of iodine and the properties of tellurium, he saw that there were some things about their properties that didn't make sense based on the column that they were located in. So as he did more research, he goes, I just think that somebody may have calculated the atomic mass wrong. Had to have calculated the atomic mass wrong. So he knew that tellurium should be in the column of oxygen, and he knew that iodine was a halogen and needed to be in with fluorine, chlorine, and bromine. So he went ahead and switched them anyway. He switched them into their proper categories and just was under the assumption that someday someone was going to prove that the atomic masses were calculated incorrectly. Well, as we started developing more elements and things started switching more and more, there was a man by the name of Henry Moseley that said, let's look at the atomic number. Let's look at the atomic number. Oh, look here. The atomic number never changes, because they found later on that protons will not change, because once you add a proton, you're changing the properties of the element. Therefore, as you add protons, that's what we're going to call the atomic number, and that's now how we're going to organize the table, okay? So that's how we flipped from atomic mass, increasing atomic mass, to increasing atomic number. And after all that, tellurium and iodine actually remained in their proper categories. So that was just another way of validating Henry Moseley's organization of the table, okay? So now in saying that, we can assume now that elements in the same group have similar physical and chemical properties about themselves, okay? Elements in the same period have a repeating set of properties, okay? So if you have the same period, a period is a row, group is a column. So when we go across a row, you have a repeating pattern, meaning that when I start on the left, all those elements on the left column are going to be the same each time I start a new row. So as you go across the row, the properties are changing based on their columns, and then when you get back to the left side again, the properties are going to repeat themselves, okay? Now, elements in the same period have a repeating set of properties. This is referred to as the periodic law, meaning every period it's going to repeat itself, okay? Now, the periodic table can be broken up into three categories: metals, nonmetals, and metalloids. So right here in the pink that you see right here, these are all of your metals. 80% of the table is made up of metals. 80%. Then you have this small portion that is touching the stair-step line, separating metals and nonmetals. These are called metalloids, or semi-metals. They have both characteristics of metals and nonmetals, okay? The only one that touches this line, okay, that is not a metalloid is aluminum. And we all know aluminum is a metal, okay? So just understand this is an exception that is touching the line, but it's not a metalloid. And these two, this row here that you don't see but is now there, okay, because now we have elements all the way up to 118. These two elements here, that's why the line does not continue down. It's because they are not considered semi-metals either, because those are considered synthetic elements, okay, man-made. Now, metals, they include good conductors. They are shiny or luster. They are solid except for mercury. Mercury is the only liquid metal. They are ductile, meaning you can draw them into wires. This is how we got all of our technology. And then malleable, they can be hammered into sheets. You're actually going to see that in lab tomorrow when we do our lab. You're going to see some malleability. We're going to hammer some metal, okay? Nonmetals. The properties of nonmetals include, they tend to be gases at room temperature. They are poor conductors of electricity except for carbon. They are brittle, meaning if I hammer them, they're going to shatter. And they are dull in color. They're not very pretty, okay? Metalloids, okay, generally have some of the properties of metals and nonmetals, okay? So they're going to have both properties, just depending upon which metalloid it is. Okay, now how to classify them. So this is what you did the other day. You classified your table. Okay, here we have our alkali metals, which are highly reactive with water, by the way. Then you have your alkaline earth. The middle section is called transition metals. We'll talk more about that later because they can transition into different oxidation states, which we'll learn about in a little bit. These are your chalcogens, right? And then you have your halogens. And then you have your noble gases. And then once again, these are your metalloids there, okay? Now, elements in the same group have similar properties because of the similar configurations, meaning this is my S1 column. This is my S2. Remember, these are all the D sublevel, transition metals. Here's my F block. This is a lanthanide and actinide series. And then my P sublevel, okay? And then my noble gases. Okay? Now, what we're going to be talking about later in the week is electron configurations are related to the following properties. Relative reactivity, how they react with other elements, ionization energy, the tendency to lose electrons, atomic radii, their size, and electronegativity, okay? How they bond with other elements, okay? So we're finished today. I hope you guys have a great Monday, and I'll see you soon.